To finish here, we've taken a look at the inputs of water to ecosystems, and we've also taken a look at the movement of water through ecosystems, through the soils, into the plants, and out of the plants, or through the plants. Lastly, we're going to take a look at some of the controls over water losses from ecosystems. Water input is a major determinant of water outputs from ecosystems. This part seems pretty simple, but you can't lose what you don't have. So the more precipitation there is, eventually the more losses there's going to be. If you don't have a lot of precipitation, losses just can't be high. Now in equation form, when you're thinking about the balance of inputs and outputs, what the authors show here is that precipitation plus or minus changes in storage need to balance with your losses. So these are your inputs and changes in storage, and then the two main loss factors, evaporation and runoff. The controls on these losses, for example, depend on a number of factors. One of those main losses are transpiration rates. And on the x-axis, we have available soil water as a percent of capacity. And you can see that the higher numbers are here. So you start at 60%, and as you get drier, 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 till you're at 0%. We have two y-axes here. The first is pre-dawn plant water potential, which is an index of water stress in the plants. And the next one is transpiration rate. And you can see that as the soils get drier, the plant water potential doesn't change too much from where it was when the soils were saturated. But once you hit a point for soil water, your soil water potential is going to change a lot, and then the plant water potential changes also. Over this entire course, that transpiration tends to be pretty similar until you get to a point when the plants start to be water stressed, and then they really start to close their stomata. So it's a nonlinear function. Transpiration can be relatively constant, then plants are going to get stressed, and they'll shut down their stomata or they'll drop their leaves, for example. And that depends on their water potential. And all of that is being driven by soil water potential and how much water is in the soils. That's one of the controls on transpiration rates. In this example they give, we talked about how evapotranspiration was one of the loss pathways. Stream flow is another. So if you take a look at across years, this is the relationship between annual water input. So this is how much water precipitation we have. The units here are liters per meter squared per year, which is the same as millimeters per year. So 1 millimeter over a meter squared is a liter of water. So here what we have are the relationship between inputs, precipitation, and output. And again, there's two sources of output, evapotranspiration and also stream flow. These are your losses from the system. Across years, evapotranspiration is relatively constant. So you only have so much leaf area, you have so much driving force, and you have a lot more water that might enter into the system, but not much more potential to transpire it. All that extra water goes into stream flow. This is for a deciduous forest. This is Hubbard Brook again, and this is over a 19-year period. And so you have a moist forest where evapotranspiration doesn't vary much across years, and stream flow is really sensitive. So there's all that extra water that comes down from precipitation that ends up in the streams because it's not being transpired, and you just don't have enough storage in the system. And you can see too with evapotranspiration that that's a slight negative decline, but over the range across years, you really don't get enough drought such that evapotranspiration declines that much. So evapotranspiration is relatively constant, and the wetter the year is, the more stream flow you have, because all that extra water that enters the bucket, the amount that is transpired is going to be pretty constant. So some years you'll just have all that extra, if you have extra water, you're going to have extra stream flow, but not extra evapotranspiration. So one note on storage is that if we think about storage of water, is that really part of the ecosystem? So if you have your bucket, there might be water at the bottom of the bucket. But is that really part of the ecosystem? So when we're doing our ecosystem budget, ecosystem water budget, how deep do we draw the box? Well, one way to think about this is really to think about whether that water is within the bucket. Because you can have water that might be at 2 meters, and you can have water that's available at 10 meters, and sometimes you have water that's available at 100 meters. And so when we're doing our ecosystem budget and thinking about changes in storage in that ecosystem versus a loss, it really has to do with the rooting depth of plant. And so if water enters the system and is stored within the rooting system of a plant, then you would consider that storage. If it goes below the rooting system of a plant, then that tends to be a loss from the system as far as how we drive it or draw it out. In that case, vegetation is important. And vegetation is important for thinking about how deep that bucket's going to be and whether water is considered to be stored or lost for that ecosystem. But vegetation has other characteristics that are really important for determining loss patterns. In these two paired figures, on the x-axis we have the area that's deforested, and that's the percentage of a watershed. And on the y-axis we have a change in stream flow. What we have, the more deforestation you have, on average, the more stream flow. So if you remember, plants transpire water. When you cut the plant down and there's no plant left, you have a lot less transpiration. That means water entering into the system, a lot less is going to transpire, more is going to run off or enter the stream through other pathways. And that's all this graph shows, is that on average, the more deforestation you have, the more stream flow that you end up getting. Now the converse of deforestation is afforestation. And what this is a change in stream flow, but with plantations of trees put into grasslands. And in this case, 10, 20, 30, 40, 50 years of tree growth on a place that was formerly grassland generates what was once a small forest now becomes a big forest. And what this represents is how much change in evapotranspiration you have. And as that forest matures and you get more leaf area and more ability to gain water, you're going to have more ability to transpire water too. And what we see is that areas that were once grassland that didn't have a lot of potential to transpire water, they get turned into plantations of trees that have a lot more ability to transpire water. And they're using water that earlier had gone into stream flow.